Hi everyone. Firstly, I would like to thank the organizer for giving me the opportunity to present my work, and also thank you all for coming to my talk. Today, I will discuss on our recent work on chemical looping ion separation and using perovskite as oxygen sorbents. Throughout this talk, firstly, I will give a brief introduction on why we are working on chemical looping ion separation. Next, I will talk about how do we select suitable oxygen sorbents for separate oxygen from air. Next, I will use perovskite as an example to demonstrate how we design low temperature oxygen sorbent. Finally, I'll give my conclusions. We all know that nitrogen and oxygen are the top two gases used in industry. For example, oxygen is widely used for production of steel, chemicals, and also is critical for coal gasification. There are also other emerging applications such as oxy-fuel combustion for CO2 capture. So the market for ion separation is huge, which totals around $38 billion per year, and also consumes a lot of energy and emitting a huge amount of CO2, which poses a serious challenge to our environment. Currently, cryogenic air separation is widely used in industry to produce oxygen from air. Using this process, air is compressed and cooling down to liquid, followed by distillation to produce gaseous oxygen. This process has many advantages, such as it can be used for large-scale oxygen production, ranging from 20 up to a few thousand tons of oxygen per day. The oxygen produced generally has very high purity, up to 99%. It also has excellent byproduct compatibility. The problem with cryogenic method is that the energy consumption is high, which requires 0.2 kilowatt to produce 1 kilogram of oxygen. So its thermodynamic efficiency is relatively low as 25%. Another major technology is pressure swing adsorption, which is generally used for small-scale oxygen production. The oxygen purity is relatively low as 95% compared to cryogenic method. Also, its energy consumption is higher as 0.5 kilowatt to produce 1 kilogram of oxygen. So it's highly desirable to explore other methods to produce oxygen in an energy efficient way. One potential method is chemical looping ion separation. The advantage of chemical looping ion separation is that the energy consumption is just a third of this cryogenic method. So that is thermodynamic efficiency, it can approach up to 75%. Another advantage is that the oxygen purity can be very high, as 99%, which is comparable to cryogenic method. The disadvantage of this chemical looping method is that the byproduct compatibility is low, which means it generally can only produce oxygen only, which is similar as a pressure swing adsorption method. So for chemical looping ion separation, it consists of two steps. One is oxidation step, the other one is reduction step. Basically, it requires an oxygen sorbent, which can release oxygen when you purge the sorbent with like steam. So it can drive the oxygen out from the sorbent and release the oxygen. And the oxygen can be separated from the steam by condensation. After this process, the sorbent is reduced, which can be reoxidized by passing air through the sorbent, so that oxygen can be stored in the sorbent, so that it can complete the cycle. So the key for this process is how to design an efficient oxygen sorbent, which can operate as reversibly by absorption or desorption of oxygen. And the the one application for this chemical looping L separation is to design a modular unit which can integrate with Next, I will talk about how do we select suitable oxygen sorbents for chemical looping L separation. As I mentioned previously, the key of chemical looping L separation process is how do we design a suitable oxygen solvent which can reversibly store and release oxygen. Initially, we have designed mixed oxide as the oxygen solvent for L separation. In this case, we have chosen cobalt iron mixed oxide and doped with perovskite. And in this case, we can achieve really high oxygen capacity. As you can see, the oxygen capacity can reach 4%, but the operation temperature is kind of relatively high as 50 degrees Celsius. Below that temperature, the oxygen capacity is really negligible. Generally speaking, transition metal oxides such as copper iron oxide has high oxygen capacity. However, the operating temperature is high as well, generally above 800 degrees Celsius. Because below that, the kinetics is really slow for particle application. That's why high-grade heat will be required in order to use transition metal oxide as oxygen solvent. In order to minimize energy consumption, it's important to design oxygen solvent which can be used at low temperature so that processed waste heat can be integrated to supply the energy. One family of material we can look at is perovskite, because perovskite has a flexibility to accommodate a large amount of oxygen vacancy within structure. Also, by changing the A side and B side elements, we can adjust their redox property. As shown in this figure, we have chosen perovskite with different A side and B side elements combination so that we can adjust their reduction enthalpy so as well their reduction temperature. Because in the end, our purpose is to select suitable oxygen solvents which can be operated on the low temperature range, which means that the solvents can release oxygen at relatively low temperature, for example at below 600 degrees Celsius. So that from here, we can choose materials which has reduction temperature at below 600 degrees Celsius. On the other hand, if the reduction temperature is too low, for example, as a case of calcium cobalt oxide, which means that it's so easily to be reduced, that means it's hard to be reoxidized. So in the end, we need certain kind of balance between redox property. And also, considering the structure stability, in the end, we choose strontium ferrite sample because it has suitable reduction temperature at around 400 degrees Celsius. And we choose this material as the basis for further modifications as our oxygen solvent. So, since we choose strontium ferrite as a base materials, so next I will demonstrate how we can further modify the materials to tune its redox property so that we can achieve the best L separation performance. From previous screening, we know that calcium and cobalt containing perovskite generally has low reduction temperature. That's why we choose these two elements as a dopant to further modify the redox property of strontium ferrite sample. So we perform DFT calculation based on pure strontium ferrite and calcium doped sample and both calcium and cobalt doped sample. We found out that by doping of calcium, the oxygen vacancy formation energy actually is decreased, and further decrease of this oxygen vacancy formation energy is achieved by co-doping of calcium and cobalt in the strontium ferrite structure. Based on these theoretical findings, we performed a temperature-programmed oxygen desorption experiment. We found out that for pure strontium ferrite sample, we have the reduction peak roughly around 460 degrees Celsius, and then there's a broad peak ranging from 500 to 700 degrees Celsius. Then by doping with calcium, which is a red curve, we found out that this first peak intensity becomes increased, which indicates more oxygen are released during this stage. And then, instead of broad peak over here, there's a sharp peak observed at roughly 570 degrees Celsius. So, which means that this calcium doped sample actually more easily to release oxygen compared to pure strontium ferrite sample. And by co-doping of calcium and cobalt, we observe that there's only one major reduction peak occurs at around 480 degrees Celsius. So it shows that by co-doping of calcium and cobalt, this sample is really easy to release all the oxygen at below 600 degrees Celsius. We did XRD characterization of the strontium ferrite samples. It shows that both a pure and a calcium cobalt doped sample shows a perfect perovskite structure. There is some lattice contraction due to doping of calcium because calcium is smaller compared to strontium. We also run in situ XRD to examine the phase transition of the pure and co-doped strontium ferrite sample in the argon atmosphere. It shows that for the pure strontium ferrite sample, the phase transition from perovskite to brown mineral phase occurs at around 510 degrees Celsius. By co-doping calcium and cobalt into the strontium ferrite structure, we actually reduced the phase transition temperature from 510 to around 390 degrees Celsius. It shows that this co-doping strategy is effective for reduce the reduction temperature, which is consistent with our theoretical calculation as well as the oxygen TPD analysis. Next, we will examine the oxygen vacancy under different operating conditions by varying the temperature and the oxygen partial pressure. Generally, the trend is that by increasing the temperature, more oxygen vacancy will be created because at high temperature, more oxygen will be released from the solvent. Oxygen vacancy can also be created by reducing the oxygen partial pressure. It is interesting to note that by doping calcium at A site, more oxygen vacancy can be created, particularly at low temperature range for oxygen partial pressure of 0.01 atm. This effect is further enhanced by co-doping calcium and cobalt. For this co-doped sample, more oxygen vacancy can be created even under oxygen partial pressure of 0.2 atm. As a result, this co-doped sample will give us highest oxygen capacity, particularly at low temperature range, and its oxygen capacity can reach above 1%, which is significant for this perovskite oxygen solvent. Since we know that co-doping calcium and cobalt can enhance oxygen release and improve oxygen capacity, we further examine the effect of cobalt concentration on the oxygen capacity of co-doped sample. The left figure shows the oxygen capacity versus temperature and the cobalt concentration. It shows that with low cobalt concentration, it gives us highest oxygen capacity only at high temperature range, while at low temperature range, their oxygen capacity is negligible. As a contrary, when we increase the cobalt loading, we can enhance their oxygen capacity at low temperature, even as low as 400 degrees Celsius. Particularly for this 60% cobalt-doped sample, it gives us oxygen capacity as high as 1.21% at 400 degrees Celsius. Similar trend was observed for temperature swing mode. Next, we studied the effect of calcium and cobalt doping on the thermodynamic property of this cold-doped sample, namely reduction enthalpy and reduction entropy, using this Van Hoff's equation. Our experiment is that we determine the oxygen vacancy at different oxygen partial pressure and temperature, so that we can obtain a set of oxygen partial pressure and temperature data under the same oxygen vacancy. And from there, we can calculate the reduction enthalpy and reduction entropy. It shows that with calcium-doped sample, the reduction enthalpy is around 24 kJ per mole, which can be reduced by co-doping calcium and cobalt to 13 kJ per mole. It shows that with doping of cobalt, we can further enhance the oxygen release. This figure shows the reduction enthalpy obtained by experimental results and DFT calculations for calcium-doped sample as well as calcium and cobalt co-doped sample. Both results show that by co-doping calcium and cobalt, we can reduce the reduction enthalpy compared to the sample with only calcium doping. And then this oxygen vacancy formation energy actually can be correlated with the electron charge on the oxygen atom. This can be understood by that with more electrons donated to oxygen atom, then extra energy will be needed to reduce the charged oxygen atom and release oxygen to the environment. We then studied the effect of cobalt doping on the kinetic property of the ionophile sample, including oxygen diffusion and the surface oxygen exchange. It shows that by co-doping of calcium and cobalt, we can significantly reduce the activation energy for both oxygen diffusion and surface oxygen exchange. For example, for the calcium-doped sample, the activation energy for oxygen diffusion is 130 kJ per mole, which can be reduced to 106 kJ per mole. As a result, both the oxygen release and oxygen storage rate can be greatly enhanced by co-doping calcium and cobalt. The stability of this co-doped sample was studied by pressure swing between argon and 20% oxygen, as well as between 5 and 15% oxygen. Both experiments show that this sample is very stable for 100 cycles oxygen production. There's no deactivation was observed. For example, at the first few cycles, the oxygen capacity is 0.94, which remains the same at the end of 100 cycles of test. The morphology of the fraction of spent co-doped sample was studied by scanning electron microscopy. It shows that the sample morphology remains almost unchanged. No sample sintering or phase separation was observed after 100 cycles of redox test. The stability of this co-doped sample was further evaluated by large-scale tests. We use roughly around 330 grams of sample with the air feed rate ranging from 1 to 3 standard liters per minute. It shows that this sample gives stable oxygen production over 10,000 cycles test. So here I give my conclusion. Basically, we have designed calcium cobalt co-doped sample, which function as an efficient low-temperature sorbent for chemical looping ion separation application. Through co-doping of the calcium cobalt, we can lower the oxygen vacancy formation energy, which is achieved by weakening the cobalt-oxygen bond. The oxygen capacity as high as 1% can be achieved at low temperature range. This cold doping also lowers the activation barrier for oxygen diffusion and surface oxygen exchange. This material is also very stable, can be used for more than 10,000 cycles tests under large-scale evaluation. Finally, I should thank my advisor, Prof. Lee, for his advice on this project, and I also thank my crew members, including Emily, uh, Dr. Xijun Wang, as well as my undergraduate student Thomas, for their help on the experiment as well as DFT calculation. I also appreciate contribution from our collaborators from West Virginia University, as well as our industry partner for their contribution in large-scale evaluation of the sorbent, as well as the ECR measurement to study the kinetic property of the cold-doped sample. Yeah, I would like to thank you all for your attention. Please feel free to ask any questions. Thank you.